Hi everyone, welcome to AWM Pitt Grad seminar. Today we have two speakers, Jenny Power and Lin Chan. Jenny Power is from University of Bath, UK, and Lin Chan is from Carnegie Mellon University. Both are PhD students in math. So Jenny will talk about making cancer treatment safer with math, optimal control for brachytherapy radiation problems, and Lin Chan will talk about an optimal mass transport method for random genetic drift problem. So we'll start with Jenny. Please, you can go ahead and share your screen.
Sure. Fantastic. I'll just confirm you all can see that. Brilliant. Okay, cool. Hi everyone, and thank you so much for the invitation to come and speak. It's really nice to, I guess, get to talk about my work to people not from my university, because I think they're quite sick of it by now. So I work on optimal control for brachytherapy radiation problems. So for our first trying to say that word, Prashana, you did quite a good job, because it's a bit tricky. I struggled with it for a while, or as I mainly like to think of it, my work is on using maths to make cancer treatment safer. So I'm a second-year PhD student at the University of Bath, and I work with Dr. Tristan Pryor and Dr. Sylvia Gazzola on this stuff. Fantastic. So my research mainly focuses on PDEs and optimization, but mainly for healthcare applications. So I'm briefly going to start with a quick introduction into what brachytherapy actually is. So most of the time when people think of radiotherapy treatments, it seems to be the general kind of sorry, I'll just set a timer so I just know how long I've been speaking for. So most of the time when people think of radiotherapy treatments, it seems to be the stereotypical external beam type of radiation. You have a clinician who targets the tumor from the outside with some sort of laser, and that is how the treatment works. Brachytherapy is slightly different in that it is internal radiation. So brachytherapy comprises of little seeds of radioactive material, which are stored in capsules, and these are then surgically placed onto the tumor themselves. So it's a really, really great form of treatment. Everything can be quite localized, and that means you get quite a high dose, right? It's actually quite efficient. So what these seeds do is they slowly emit radiation, killing the tumor from the inside. The main types of cancers this is used for is kind of like, I guess, cancers in the hard to reach places, I suppose. Primarily cervical cancer, certain types of eye cancer, particularly like back of the eye, prostate cancer, and certain instances of breast cancer as well. So like I said, you can have a really, really high dose rate because everything is so localized in one region, which makes it quite efficient as you can really focus in on the tumor. There is one issue with this, unfortunately, is that I suppose this is for, we're using this for when we're inside treating tumors inside the human body, which is not an isolated system. There's going to be other stuff surrounding the tumors, like normal healthy tissue, critical organs, which we do not want to be exposed to the radiation. It could be the instance where you really, really localize and put so much radiation on the tumor, but then in the process you end up damaging an organ, and you're almost kind of slightly worse off than you were if you weren't to use radiation at all. So my research, I'll quickly go over just the schematic before I move on. You can see here in green, we have this tumor. The red dots are these like radiation seeds. So they're kind of like, you place them directly on points in the tumor. And then you have healthy organs and surrounding tissue around it. My research question essentially is, where can we place these radioactive seeds that we can minimize the damage to surrounding organs and healthy tissue, while still ensuring that the tumor has enough radiation to kill it, right? So it's kind of like a balancing act. We want to make sure that the tumor is gone and that our treatment is effective and that we can eradicate the tumor fully, or as much as we can, but we don't want to cause excessive damage to any of the surrounding structures. So it's kind of like a balancing act. You might be reading this question thinking, It's kind of, we're looking for like an optimal solution. It kind of sounds like an optimization problem. It is. So in particular, it's a PD constraint optimization problem. So in general, what we want to do is minimize some cost functional given here by J, subject to some PD constraint being satisfied, right? And that PD constraint here is given by U. So you can generally split PD constraint optimization, or PDECO as I might refer to going forward. You have two variables that you need to consider. You have your control variable, which we represent here by F, which is what we can control. We can change it, fix it, and all that sort of stuff. And then our state variable, U, which is dependent on F, if you will. It's kind of, we change F, that affects U. So this is kind of the general layout. What does this actually mean for us and for our problem? So our PDE here, our PD constraint, is an equation which represents the radiation in our domain. So particularly, I'm going to be using a diffusion approximation for a radiation transport equation. So this is the Boltzmann transport equation, if you're familiar with it. But you can kind of think of it going forward as just a simple diffusion equation. And this is for the radiation flux in our domain. So our cost functional then, it's going to be designed in such a way that when it minimizes it, the radiation flux will match a given dose, right? So in theory, you'll be given some sort of maximum dose limit by the clinician, being like, we can only give radiation up to this amount in the body. So the cost functional will take that into account. So then when it's minimized, it aims to make sure that the radiation in the tumor matches this dose. For an ideal configuration of radioactive seeds, by this I mean number, positioning of them, and also the strength, right? They can do kind of like really, really big ones with a lot of radiation, or like half strength, that sort of stuff is allowed. Numerically, then, the main tools that I do use for solving the PDE system and all of that, I mainly use the finite element method. I'm not really going to touch on it or any of that sort of stuff in the presentation. It's just for anyone who wants to know what I use for simulations, all that sort of stuff. It's finite element method, and mainly I use Firedrake with Python to solve all my stuff. So let's go into it a little bit more. Here we're looking at our Four model, or our PD constraint. This is our diffusion approximation for our radiation transport. So like I said, we have two main variables to consider here. We have U and we have F. So U is our radiation flux density in our domain. So you can kind of think of this, if you will, as like the dose in the domain, how much radiation is everywhere. It's not exactly the dose, but they work in quite a similar way. That's fine to kind of think of it that way. So it's like, in my domain, how much radiation is everywhere. F, on the other hand, is our radiation source impact, if you will. It's if I place a seed in a certain location, this is how it's going to spread in space. That is what F represents. So some other things to mention here, which I think are, I guess, a little bit important. Omega here is our domain. I've just posed everything in R2. This will extend quite nicely to R3, and also works in 1D. Mu A here is our absorption coefficient. You can kind of think of it as how well tissue will absorb the radiation, right? And then our diffusion coefficients D also depend on this parameter. So it's basically, we have certain types of tissue that absorb radiation really, really well, but if they absorb the radiation, it means it's gone and it can't spread anywhere else. So that's kind of what that takes into account. You can kind of see what I mean a little bit better if we look at the figures here. So on the very right-hand side, we have this mock CT scan, if you will. So this is actually the Shep-Logan phantom, if anyone has come across that before from imaging methods. It's quite a test image that's used quite often for kind of medical imaging algorithm tests. But this is supposed to give like a mock CT scan of the head. So the way CT scans work is that the brighter a pixel is, the denser the tissue. So the white pixels here represent, you can think of it as bone, right? Really, really dense tissue, whereas the darker pixels represent like soft matter or gray matter and stuff like that inside the brain. What it actually is doesn't really matter. It just, yeah, bright pixel, really, really dense, radiation won't spread through it very easily. Low, dull pixel is radiation will spread quite through it. Fantastic. So on the left then in our simulation, this gives the radiation flux throughout the domain. So this is in the instance where we've placed a radioactive seed at this red dot here inside of our phantom. So as you can see, the radiation disperses through the domain. You do have this sort of like barrier surrounding kind of where the skull tissue would be. So the radiation doesn't go any further from that, which is, I guess, quite nice. And the radiation seems to be the most localized where our seed is. So this is how our forward model operates. Let's move on to designing our cost functional. So we can split our cost functional into 3 different parts. We'll start first off with our tumor constraint. So this is the constraint that enforces that our radiation flux matches the prescribed dose for our tumor. Okay, so if we are to ignore the other 2 terms and just worry about minimizing the first term, it's a norm. So when its smallest value is 0. So when this is equal to 0, it means U is equal to dt, right? So that's what that constraint focuses on. However, as we kind of are aware, I said before, this is a balancing act. We're not just worried about making sure the tumor has enough radiation. We also want to make sure that the radiation in the other tissues is minimum. And this is what our second term deals with. So we have a summation here. So this is to account for n number of tissues in our system. So let's just focus, let's say, just on the L2 norm. So this is for 1 tissue. When this norm is minimized, it enforces that U is equal to 0. So the radiation is 0. The different lambdas then enforce how strong we want the condition to be, right? It's kind of that balancing act. If lambda is really, really big, relevant to the tumor constraint, it's like, this is the most important thing to focus on minimizing. That's what it tells our cost functional. So it is kind of just basically lets us know, the cost functional know for our optimization algorithm, which are the more important terms to worry about making 0. Okay, our final term then is our regularization term. This is just in to make sure that everything is well posed. So our solution exists, it's unique, and it's stable. We regularize here with F. This is quite standard in the PD constraint optimization literature. So this is what we have went for. The figures then at the bottom give the case where it's a 2 tissue example, and we'll come back to that later on in the presentation, but it's kind of when we're thinking like we have a tumor at the center of our domain and everything around it is normal, healthy tissue. So in this kind of case, we basically ignore the middle term and we just focus on optimizing the tumor constraint and the regularization term. We end up with a nice, like globally, like it's a convex cost functional, and our tumor constraint, oh god, the light does that sometimes. It's 9 p.m. So I'll just do that. Oh, sorry. There we go. Awesome, that's fixed. I knew that was going to happen as well. It's automatic. Anyways, you can think of it, we have this sort of like on-off function for our tumor constraint. It's 0 outside of our tumor and it's on in our tumor. Lovely stuff. Last but not least, we have one final constraint to deal with, okay? So as I kind of hinted at before, we are optimizing for the position of the radioactive seeds. We do not have any control over the shape of F. So F is how the radiation spreads in space, right? When you place a seed down in a certain position. This is already predetermined from physics. So we have no control over this. So this does mean that we have to add in some additional constraints to our problem. We can only control where we place the radioactive seeds. So instead, what we have to do is we enforce another condition that f should be some linear combination of shape functions, right? Going forward, I will use Gaussians because it's the closest physically. I think empirically they measured it to be some sort of weird radial quintic thing, but Gaussians is an okay enough approximation, so we're gonna go with that. But basically, it's that my whatever radiation source I get, it has to be some sort of linear combination of loads of Gaussians in different areas. So the figure at the very top there gives an example of what an example F could look like, right? The seed is placed here at this pink dot, and then the black curve is what F looks like because of that. So we can't change the shape of F, we can only change where we place the pink dot. So these WIs here, sorry, that should be I is 1 to n, not n to n. But these I's here, these WIs are our weight functions, right? So if I have, let's say, a grid of possible places I can place seeds, it will tell me, okay, in this position over here, I don't want any seeds. I'm going to have a weight of 0. In a different position, I definitely want a seed there. It's going to have a weight of 1. And that's kind of how we end up figuring out where we have. And theoretically, then we'll end up with some sort of solution F that takes some sort of shape like the blue curve here in the bottom figure. So this curve here, I have 3 seeds placed in XS, XS2, and XS3. So you can see this is kind of the linear combination of loads of different Gaussian functions. So in certain areas, the weights are bigger than others, and that's kind of what gives you this kind of weird bumpy looking shape. So this is what we're hoping for altogether. Fantastic. I guess now, how do we solve PD constraint optimization problems? So there's a few different ways of doing it. My preferred method is to use a Lagrangian formulation. So this treats U and F as our state and our control as independent variables. There's another method which reduces it to just a one variable system, but I prefer this way. So we have to do this. We need to construct some sort of Lagrangian functional. This is given by our cost functional minus the duality pairing of our PDE with some Lagrange multiplier. In our case, actually, it's quite nice. The Lagrange multiplier Z does end up being the adjoint variable for the adjoint equation of our original radiation PDE. So that's quite nice. So when do we have an optimal solution? We need to enforce some optimality conditions. And these are just given by these first order derivatives here. It basically means that the derivatives of our Lagrangian functional in all 3 variables, our control, our state, and our adjoint all have to be equal to 0. Okay, so this is quite clearly seen in the case on the left. I've posed 2 different sets of equations here. The left is when we have no control constraints. So this is the case where we don't care about the shape of F, right? We're not too worried about that. We just want an optimal F. This is not a physical case because we can't actually do that in practice. But we just end up with this lovely linear system that we can solve. When we do actually take into consideration that F has to belong to a certain admissible set of functions, then our system gets a little bit more complicated. The first 2 equations in both are the same, but it's our final equation that is different. On the left, we have a linear equation. On the right, we have a variational inequality. So this takes our lovely, nice linear system and makes it a little bit trickier to solve. So this variational inequality basically imposes that F belongs to that subset. Brilliant. So let's get onto some numerical simulations, and in particular, I'm going to introduce now a simplified setup. Okay, so this is the 2-tissue system that I was talking about before. We have a tumor at the center of our domain here, and then everything that is not our tumor is normal healthy tissue. Okay, we simplified our PDE a little bit as well. We're just using uniform diffusion. So our PD just reduces to this. And once again, we're modeling each seed as a Gaussian function. So where XS here gives the position of the seed, For this system, it might be like intuitively clear to see that the position of the seed, or even just one seed, that is going to minimize radiation to everywhere that's outside of our tumor is at the center. We're dealing with a circular tumor here, so the point that is furthest away from outside of the circle is the center of the circle. So intuitively, we know that that is what the answer should be. So this is kind of a test case I've been working on just to make sure that my algorithm is working and all of that sort of stuff. So our optimality conditions for this case, I'm going to first show you results for the case when we have no control constraints. So F is not restricted to be a Gaussian or anything like that. It can take on any shape. So this is our Lagrangian functional, and we have our three optimality conditions here posed weakly. So like you can see, we have a linear system. For solving this, we simply just solve a linear system for U, Z, and F. Okay, A here is our operator that's associated with our forward PDE. A star is the adjoint operator for that same PDE, but for the adjoint equation. And M here is a mass matrix, which takes into account the kind of L2 inner products that we have from, let's say, FV here, and our third compatibility equation also. So this is lovely and nice. We just solve this linear system. And here is some of the results that we get from this case. Okay, so on the left, we have an image of the computed F, so given in blue, and I've called it F ideal, but it's really just what one Gaussian actually looks like. Okay, it's not necessarily the ideal case. It's just if we had one seed, if it's constrained, that's what it should be. Okay. And on the right then, in orange, we have our target, okay? So it's on in the tumor area and it's off, so it's 0 outside of our tumor. And then blue gives the U that matches that from the computed F, okay? So this is all fine, except obviously this is not physical for the main reason, not only taking into account that we actually can never get this type of a distribution because that's not how the radiation seeds work. We can't control the shape of F. We also get areas where the radiation is negative, which is really, really non-physical. We cannot have negative radiation. So that's one thing already that is like, yeah, it's not really going to cut it, particularly for actual clinical applications. So then we kind of have to go in and focus a little bit more on the control constraint case. So this is our Lagrangian functional for this case. And as you can see, our compatibility condition now is this variational inequality. So what is the algorithm for solving this? It's a bit more complicated. We can't just solve a linear system anymore. We have to do a little bit more. The way that I'm currently tackling this is iteratively. So we first solve the forward PDE. Okay, so given some initial guess for our source, we solve the forward PDE to get some guess for U. And so our flux, we then solve the adjoint PDE to get an estimate for Z, our adjoint, and then we can compute the updated source using a fixed point method, where PR here is a projection into the admissible set of possible functions for F. Okay, so this is what it does here. Omega is a relaxation parameter, which kind of just ranges kind of what it's kind of in there, sort of like you can kind of think of it like a step size, but it's not quite that. Fantastic. So what are some of the results from this method then? They're a work in progress. So one thing we have shown is that this variational inequality fixed point method for solving the variational qualities, because the variational qualities aren't easy to solve numerically. There's a lot of theoretical results around variational qualities, but personally anyways, feel free to contradict. I haven't seen a lot of stuff about actually implementing them. But we did show that this method anyways, just for the variational inequality step, does have an iteration error estimate of this given here. So it's the L2 norm squared of the k plus 1th iterate minus the actual exact solution is omega minus 1 squared of the previous the L2 norm of the previous iteration versus minus the true solution squared. And we showed as well that omega has to be in the range of 0 to 2 in order for this to converge. Okay, so that means if it's in between 0 and 2, it means the next iterate is the error is smaller than the previous one. This is kind of a figure here of my implementation for solving the variational inequality. So basically this is if I have some sort of piecewise function, this is like the best sum of Gaussians that best approximates that function. Okay, so that's kind of was quite nice. I was quite happy with that actually. But as for the full system, solving it, it's currently a work in progress. The error analysis seems to be quite tricky at the moment anyways, just because there's so many steps and there's a lot of stuff to take into account. And I still don't have it fully converging yet. So I don't know, check back in whenever, then I'll hopefully have that solved. But so far anyways, this is kind of where we are with implementing the control constraints. So some conclusions and plans for future work. So far, we have an algorithm which gives an ideal radiation distribution in the domain. Okay, so in an ideal case where we're not worried about shapes or like anything actually physical, this would be the best way to distribute the radiation in the domain. However, this model isn't physical. So my current next step anyways is finish implementing the control constraint approach, do some error analysis on it, some convergent estimate, and try and get an algorithm that is working well. Another thing, which is quite nice, which I didn't really touch on at all actually during the talk, but is another aspect that I'm focusing on and we have some quite nice results for, is analyzing our choice of regularization. So currently I'm regularizing in the L2 norm. However, we are trying to approximate close to a piecewise function, right? Which is not smooth. So if we use a weaker choice of regularizer, this is going to allow us to get a better approximation to our dose constraint. Okay, so on the right-hand side here, I have illustrations of this actually. This is the exact same setup, the only for the problem. So this is the non-constrained problem. This is the exact same setup, everything is the same, except that in the top figure, I'm using L2 regularization, and in the bottom figure, I'm using H-1 regularization. So H-1 is much weaker than L2, and you can see for the same regularization parameter, I get a much better approximation to this piecewise function from H-1 than I do from L2. So this is really nice and kind of want to look into this a bit more. Another aspect then, like I said, is the convergence analysis for all of for the algorithms, but also investigating the relationships between my regularization parameter, my iteration number, the number of like possible seeds that I give as well, n. I can kind of choose a Cartesian grid of potential places for seeds if I want. So sort of analyzing the relationship between that and the algorithm, but how all of this relates to my final element mesh size as well is quite important, and that is definitely in the plans for future work. I kind of want to just end briefly on what my hopes that I think anyways could potentially come out of this work, and what I think could be quite nice. If this is to ever be, I guess, robust enough that can actually be used in clinic. It would be, of course, to aid in treatment planning, not to completely replace treatment planning, because that would be very, very unethical. But in general, the kind of process would be a patient would get a CT scan, then the relevant information would be taken from that CT scan, like our diffusion coefficients and all this sort of stuff. We feed that information into the algorithm. The algorithm outputs the optimal placements and number of radiation seeds for treating this patient, and then this information is given to the clinician to help them create their treatment plan. That is kind of the broad goal of this kind of research. Obviously, this is definitely a very, very long way away, but could be very nice. Anyways, that was my talk anyways. Thank you so much for listening. If you want to contact me, my socials and my email are there, and also a link to my research page of my website, and I'm really happy to take any questions. Thanks.
Thank you so much, Jenny.